All right, so yesterday we finished up kind of talking about this heat engine and why the short pipe going into the warm water and the long pipe going into the deep water wouldn't really work. Okay, and we said that's because that water that they're both in is already in contact with itself. Okay, the hot with the cold, so there's already a circulation going on there. There's absolutely no reason for it to go through the heat engine. The other thing we said is this doesn't work unless there's a huge difference in temperature. Right? Because the bigger the difference, the more the flow. All right? We said that the second law of thermodynamics is that heat flows from hot to cold. All right? The hotter the hot is, the colder the cold is, the greater the flow between them. All right? Because they're always trying to achieve a what? Yeah, an equilibrium, a state of equilibrium where they are balanced, okay? And in nature, you almost never achieve that. That's why there's always constant movement, okay? But again, the greater the difference, the greater the flow between, and that's the principle behind a jet engine. Okay, a jet engine is a heat engine, but in the middle of the engine, where the combustion chamber is, okay, where the kerosene or JP5 jet fuel, okay, is burned, is really, really, really hot. All right, and so heat flows away from that out the back of the engine into the cold air. All right, the comparatively cold air, even if it's 35 or 40 degrees, it's still cold compared to the temperature of the combustion chamber. All right, and so the air flows through there, and as it flows through, it draws air in through the front of the engine, which supplies more oxygen to the combustion chamber, and you get these fan blades, these turbines, spinning really, really fast and creating a really high-speed wind, essentially blowing wind out the back of this engine, creating thrust. Okay, is everybody following me there? Right? But again, it doesn't just happen if you have warm air and cold air, right? There's not really a motivation then for the air to move through. Okay? But if there's a big difference, it will move powerfully, and then you'll get this thrust being formed. Everybody follow me there? Okay. Now your refrigerator, air conditioner is different. It's what we call a heat pump. And a heat pump goes against the second law of thermodynamics. So where a heat engine is kind of like diffusion, where it's always going from high to low, a heat pump is like active transport. Right? It is pumping heat from a cold area to a hot area. Right? To do that, you're going to have to use what? Energy. It's not a natural process. Okay? So what happens is, in the back of your fridge, okay, and I don't have the picture here, it's on the next page. Okay, in your fridge, there are these little tubes, okay, that you can see here. Right, and they run through the back as well. You can see them. They're on top here. Okay, they run through the walls. They're filled with coolant. It's not Freon. It used to be Freon, but it's not anymore because it's bad for the ozone layer. Now it's some CFC-free refrigerant. Okay, and it runs through there, and as it picks up heat from the food that's inside, it changes state. And it changes state from a liquid into a gas. It takes a lot of energy to change state, okay, from liquid to gas. To give you some idea, to change 1 gram, that's 1 milliliter of water, from a liquid to a gas, already at 100 degrees Celsius, so I haven't had to change its temperature, it's already 100 degrees Celsius, takes 333 joules of energy. Sorry, 1,246 joules of energy to change 1 milliliter of water into a gas, already at 100 degrees. All right, so changing something from a liquid to a gas takes a lot of energy. It's different for every material, okay? But for your refrigerator, the coolant changes to a gas, and then it gets sent back to this compressor. All right, so it's absorbed some energy in a change of state. Then it goes to the compressor, and the compressor does exactly what its name implies: compresses it. It puts it under extreme pressure. Right? And something that you'll learn next year in Mr. Reel or Mr. Batchak's Chem 20 class is Charles' Law, or Boyle's Law. Okay? When you compress a gas, if you compress it hard enough, you can turn it back into a liquid if you put it under enough pressure. When you do that, what gets released? The heat. Yeah, all the heat that was used to turn that liquid into a gas gets released because now you've forced it back into its liquid state. It has to give up that energy. Okay? It can't hold it anymore. So when the compressor compresses it back to a liquid, heat radiates out from the compressor. And that's why if you stand right here, you can feel hot air blowing out from underneath your fridge. Right? The fan is blowing that hot air that it has taken from the fridge into the hotter area. Okay? That is the environment of your house. Right? Because obviously it's hotter in your house than it is in the fridge, and we're taking more energy from a cold area and trying to pump it away into a hot area. Your air conditioner, if you have one, does the same thing. Okay? It takes heat from your home, from the air in your home, and uses it to change the state of the refrigerant, compresses the refrigerant back, and then blows the hot air outside with a fan. Right? It requires energy for that to happen because you're going against the second law of thermodynamics. Does that make some sense? Okay. Now, the other thing we can do, someone has discovered this, is you can make a thermoelectric converter as well. Okay, it's called a thermocouple. And you can actually use water of different temperatures to generate enough power to turn a fan blade. Okay? How long will that fan blade turn? Until those two are the same. Right now you've got one that's 90 degrees Celsius and one that's 10 degrees Celsius, so it'll spin until they're very close to the same temperature. And then since there's no flow in one direction, it'll eventually just stop. Okay, does that sort of make sense? How would I reverse the direction of the fan? Yeah, change the cups. If I put the hot cup over on the left instead of on the right, fan spin the other way. John, question? No? Okay. All right, so that's a thermoelectric converter, okay? And like I said, it just shows that heat always flows in one direction. You can make that happen. Now, something like this wouldn't work very well because, again, where's the path of least resistance for heat from the 90-degree beaker to the 10-degree beaker? Where's the path of least resistance? Through the motor or straight across? Straight across. Okay? And if you put something hot next to something cold, I mean, it doesn't take a rocket scientist to figure out what's going to happen. All right? Everything takes the path of least resistance. All right. So back to this heat pump idea here. Okay? Kind of explain there how that works. Okay? Now, here's what I want you to do. There's a few questions on this first section on thermodynamics and systems, okay, that we were talking about the other day. All right. So what I want you to do are these questions here. I want you to do number 1, number 3, number 2. 4, 7, 8, 'Just have you do those ones. Okay? So I'll give you a few minutes. We should have time to get you through those and go over them and maybe get started on the second half of this thing. Okay? Since we only have till 9:26 today. Okay. All right. So, what's the meaning of the word thermodynamics? Moving of heat, changing of energy. Okay. The reason we want to kind of not just say heat is because heat is a transfer of what kind of energy? Thermal energy. Okay. There's another kind of energy that gets transferred, mechanical energy, and we call a transfer of mechanical energy, starts with W, work. Okay. So thermodynamics is the study of the movement of energy of all kinds, okay, whether it's work or heat, because the two are intimately related. Okay, usually when you do work, thermal energy gets released, so heat is transferred, right? Okay. All right. For number 2, state the first law of thermodynamics. All right, Brett. Right. Energy cannot be created, it cannot be destroyed. It can be converted, it can be transferred. Okay? That's the first law of thermodynamics. All right. And we just talked about number 3, the distinction between work and heat. They're both transfers of energy. That they have in common. It's the type of energy they transfer that is different. Okay? Heat is a transfer of thermal energy. Work is a transfer of mechanical energy. And it is a very important concept for you to know. All right? This comes up again and again all through Chemistry 20, Physics 20, Physics 30, Chemistry 30, and even in Bio. Okay? When you're talking about energy and ecosystems and food chains and things like that. This is one of those overarching concepts that you will get haunted by your entire high school science career and after. Okay? All right. For number 4, identify whether each of the following is best explained by the first or second law of thermodynamics. Okay, a bouncing ball eventually comes to rest on the floor. Okay, so energy can't be created or destroyed. Or the second law, what's the second law? Maybe we should talk about that before we... Right, energy always flows from high energy to low energy, which is why a ball eventually comes to rest. A state of equilibrium is achieved because the high energy ball is continually transferring energy away out of the system. Every time it bounces, there's some heat generated, there's sound generated, okay? Those all represent it transferring energy away, and so it eventually comes to rest on the floor. All right? A metal spoon eventually becomes hot when placed in a pot of boiling water. Maddie? Second law, again. Heat always flows from, or energy always flows from high energy to low energy. And obviously C has got to be the first law because that is the first law. Energy cannot be created or destroyed. Okay, state the second law of thermodynamics. Well, that question probably should have come before question number 4. It would have made more sense there. Okay, since we've already talked about it, second law of thermodynamics talks about the direction of energy flow. Okay, it goes from high to low. Okay, number 8. 2 sticks are rubbed together and ignite. Is the work being done on the sticks positive or negative work? Okay, now here's the thing about positive or negative work. It's from the point of view of the objects. If you are getting hotter, are you gaining energy or losing energy? You're gaining it. That's positive work. Okay? If you are doing work on something and causing energy to be lost from yourself because it went to something else, from your point of view, that is negative work because you have lost energy. Okay? You have given it to something else. So if you are rubbing 2 sticks together, the mechanical energy is coming from you. Okay? You're moving the 2 sticks. From your point of view, that's negative work. But from the point of view of the sticks, it's positive. They're getting hotter. They're taking the mechanical energy that you are using and turning it into not heat, thermal energy. Okay, that's that thing. We got to break that habit. Even I do it. I find myself doing it sometimes, saying it's heat, but heat isn't a form of energy. It's a transfer of thermal energy. Okay, for number 9, water is observed to condense on the outside of a cold glass. Which way is heat flowing? Which is hotter, the water in the cold glass or the air outside? The air outside. So, if there is water condensing on the outside, is that evidence that the water vapor in the air has lost energy? Yeah, because a gas loses energy, it turns into a liquid. The energy is being transferred to the glass. The water in the glass is warming up, and the evidence of that is that the water vapor in the air is changing state as it happens, condensing on the glass. All right, so it is evidence that there is energy transfer going on and that it is going from the water vapor in the air, or the heat in the air, or the thermal energy in the air, okay, into the glass. Okay, and can you cool a room down by opening the refrigerator door? No, because it's trying to pump the heat in there. You ask Homer Simpson, that's how he killed his refrigerator. Heat is flowing into the glass. Yeah. Okay, have a good weekend, guys. A good long weekend, but not too good. Okay? Try and get to Remembrance Day service other than the one today. Okay? Veterans deserve respect.